afternoon and welcome to the first of this afternoon's sessions. I'm Sarah Johnson and I'll be chairing this session. This session will explore the importance of sphagnum moss in the fight against climate change, and we'll also share results from the reintroduction of sphagnum as part of peatland restoration works, as well as results from carbon farming trials in Lancashire. And finally, but no least last, we'll also be sharing experiences of some rethinking of farmed lowland peat. So shortly we'll hear a series from a series of experts in the field of peat restoration and sphagnum moss and farming, after which we'll have a live Q&A session. Before that, just some brief housekeeping. As with other sessions, please use the Q&A panel to ask a question, and we'll try to answer as many as we can. Any questions that don't get answered during the session, they'll be put up on the conference notice board for further comments. So the first speakers I'd like to introduce are Andrew Davidson and Neal Wright from BeadaMoss, or otherwise known as Micropropagation Services. Dr. Neal Wright, he's been CEO of Micropropagation Services, now known as BeadaMoss, for 35 years. He's been actively involved in various sphagnum trials and spent 15 years on sphagnum micropropagation R&D. And the business has supplied over 8 million sustainably produced sphagnum beta hummock for over 7,000 hectares of restored peat. I mean, that's an incredible achievement itself. Andrew Davidson has worked in nature conservation and horticulture in South Africa and the USA for many years. So I guess the climate would have been a bit different than in the north of England, where I am now. And he's been involved in numerous afforestation and reforestation projects in South Africa. But he's now passionately supporting BeadaMoss in their quest to find nature-based solutions to protect and restore peatlands. And the video from the two of them will start shortly.
Hello, my name's Neal Wright from BeadaMoss. I will be available for question and answers after the presentations, but first I'd like to introduce you to Andrew Davidson, who is heading up our business development. Thank you.
Thank you, Neal. In the 2 months that I've been with BeadaMoss, I've absolutely fallen in love with sphagnum moss, which in my mind is a miracle plant and possibly one of the most important plants on earth. Now, as a horticulturist and a conservationist, I can see the potential of sphagnum moss to make an enormous difference in the fight against climate change. As you know, a fully functional, healthy peatland is the most space-efficient, long-term carbon store and sink. Now, damaged peatlands cover a relatively small part of the world, but contribute a massive 5.6% of the global anthropogenic CO2 emissions. Let's put that into perspective. These emissions are roughly equivalent to all the global emissions from all the world's air traffic and marine traffic put together. Now, if you want a graphic representation of the scale of this, let's look at the global air and marine traffic at a typical moment in time. As you can see, there's a lot of air and marine traffic happening around the world. The emissions from them are absolutely immense. Now let's take a look at the CO2 emissions and uptake with various levels of sphagnum cover at the Little Walden Moss site in Manchester. As you can see, without sphagnum, the restored area was still emitting some CO2 with no uptake. But with an increasing amount of sphagnum cover, it went from emitting to a net CO2 uptake. With the full cover of sphagnum, the emissions stopped and carbon was sequestered. So it stands to reason that fully restoring peatlands is an area of low-hanging fruit. If we are going to have a fighting chance of limiting warming to 1.5 degrees above pre-industrial levels, we're going to have to not only pull out all the stops, but certainly take advantage of the low-hanging fruit, the relatively easily implemented solutions. Global warming of 1.5 degrees is not safe, and we will have numerous consequences. But limiting this is the best we can do right now. Allowing it to exceed this will make adaptation drastically more difficult will further increase the intensity and frequency of extreme weather-related events and will have more profound effects on biodiversity, food security, and many other extreme consequences. The difference between a warming of 1.5 and 2 degrees, however, will be much worse, and we must do all we can to cap it at the 1.5 degree limit. In response to the climate emergency, BeadaMoss set out to find a nature-based solution and have spent years of R&D to come up with the best way of producing sphagnum moss sustainably for peatland restoration without having to harvest it from the intact peatlands in a form that makes it easy to plant and successfully cover the areas as quickly as possible. From this, the micropropagated Beada hummock was born. And that's what they look like. That's a roll of 20 Beada hummock. Being micropropagated, apart from the initial few strands of each species, we won't have to disturb any donor sites. From those few strands, we bulk up at scale in our facility. Each Beada hummock contains a clump of sphagnum moss. There are a number of recipes which contain from 5 to 11 different species of sphagnum in each Beada hummock, and the choice of recipes obviously depends on the area. Now, besides the benefits of species diversity, the spectrum of species maximizes success of cover because there'll be numerous microclimates in each planting area, and the species best suited to each spot will do the best. Over the years, we have worked closely with and supplied Beada hummock to a number of organizations doing peatland restoration, including Moors for the Future, who have planted over 2.6 million Beada hummock on 2,200 hectares on just their Moorlife project. Let's look at the results of a trial that measured the speed of cover of micropropagated Beada hummock sphagnum versus wild harvested sphagnum. As you can see, the graph shows that the cover of the micropropagated Beada hummock sphagnum covered the area far faster than the wild harvested sphagnum did. Looking at the next graph, we can see that the photosynthetic activity for the micropropagated sphagnum was substantially higher than the harvested sphagnum. The sequestration ability of micropropagated sphagnum would also therefore be higher than the wild harvested sphagnum. At BeadaMoss, we are doing our best to make sure that the production process is as green as possible. So we, for example, use solar power, as well as ground source heat pumps, rainwater collection, heat recovery, and of course, recycling. Even our nursery is in essence recycled as it's secondhand. This is in an effort to make sure that our endeavors are in fact leading to overall emission reductions, not adding to them. In the last 3 years, we've supplied over 8 million Beada hummock, and we've recently doubled our facility to gear up for the increasing need so that we'll be able to do our bit to support your peatland restoration projects and help keep warming under 1.5 degrees. Sphagnum moss also gives resilience to peatlands. According to the Committee on Climate Change's document, Land Use Policies for a Net Zero UK, peatlands in good condition with a healthy sphagnum layer are more likely to have a better chance of withstanding the hot and dry conditions that are projected with climate change in the future. So because sphagnum moss holds onto large quantities of water, having a cover of sphagnum on restored peatlands means that the peatlands don't dry out nearly as easily, making them more resistant to the effects of drought, either naturally occurring drought or due to the effects of damage mankind has already inflicted on our climate, damage that we must plan for and prepare our peatlands for. If they dry out, they will not be able to hold on to the stored carbon. So sphagnum will therefore protect the valuable restoration work that you're doing for the long term. Some other benefits of sphagnum cover include water quality improvement, especially the removal of organic carbon, which water companies are finding costly to remove, flood mitigation, as well as bolstering biodiversity. Let's have a look at a short video. That's a real graphic representation, and no words are needed to understand the importance of sphagnum in terms of water holding, runoff, and the associated erosion with all its implications. Now, let me ask you a question. What is the real cost of not taking all the action that we know of now? Even just looking at the monetary value of the measures we'd have to put in place later to shield us from the effects of severe climate change is huge. Far, far more than the amount we'd have to spend now to keep our global warming under 1.5 degrees. For example, how much would it cost to install some sort of engineering project to protect us from floods? Nature does this for free, but we must spend wisely. And although there is a cost associated with producing sphagnum moss, it is much, much smaller than the alternative. Let's do this properly. After all, we won't have a second chance. We must get it right the first time.
Thank you, Andrew, for your presentation. For those of you who don't know, I'm Neal and Barbara's daughter, and I pretty much grew up on peat bogs. As one of the youngest members of the BeadaMoss team, I just wanted to have a couple of concluding remarks. I'd like to ask that everybody starts treating climate change, global warming, whatever you want to call it, as a crisis. It is a climate crisis, and it will affect everybody everywhere. We've shown in the past year and a half what we can do in a pandemic crisis. Always hitting the news, always talking about it, all doing all we can to stop it. And that's exactly what we need to do. We're at 1.1 degrees C now. We're aiming for 1.5, which is not actually going to be safe. We are already starting to talk about below 2, not 1.5 anymore. How long will it be until we start talking about trying to limit it to below 2.5 or below 3 or even below 4 or 5 or 6? It's unfathomable, and we need to do all we can. So I hope that you all keep advocating for peatlands, keep up all the hard work that we're seeing at this conference. And together, we have a real chance of making a real impact in this crisis. Thank you.
Wow, what an inspiring end to that video. Thank you very much to Andrew and the rest of the BeadaMoss team for that really interesting talk. And I love that video actually, which showed sort of the slow flow capabilities of what vegetation can do on peatlands, like sphagnum moss. That was great. But thanks. Right, next up we have Tia Crouch from the Moors for Future Partnership Science and Monitoring team. Tia joined the Moors for Future Partnership in 2010 after graduating with an MSc in Biodiversity and Conservation and a BSc in Environmental Science. During this time, she's worked on a wide range of science projects relating to water quality, water flow, plant disease, sphagnum reintroduction, and most recently earth observation. So what a great range of experience and skills you must have, Tia. So we'll now listen to a video from Tia. Thank you.
Hi, my name's Tia Crouch, and I'm a Senior Research and Monitoring Officer at Moors for the Future. Over the last 7 years, Moors for the Future have set up a number of trials to monitor the success of sphagnum reintroduction to revegetated blanket bog. I'm going to give you a brief introduction to the various trials, and then I'll hand over to my colleague Jemma Benson, who will talk you through the results. So there are 3 trials that we're going to be talking about today: the sphagnum propagule trial, the dense plug plant trial, and the topography trial. They are all located on the north edge of Kinder Scout, which is shown in this map, and this sits within the Ashup River catchment in the Upper Derwent Valley in Derbyshire. The first 2 trials were set up in 2015, and the topography trial was set up later in 2018. The aim of the sphagnum propagule trial was to compare the establishment, survival and growth of different sphagnum propagule types on revegetated bare peat. The aim of the dense plug plant trial was to evidence how quickly comprehensive sphagnum could be achieved, and the aim of the topography trial was to investigate the effect of topography on sphagnum species. In the sphagnum propagule trial, 4 1 hectare headwater microcatchments were treated with one of 4 different sphagnum propagule types: beads, gel, plugs, and translocated clumps. A 5th microcatchment received no treatment and provided a control. These applications were replicated 3 times, as you can see on the map, in Area 1, Area 2 and Area 3. And in each of the microcatchments, 10 quadrats were set up, with each quadrat receiving a standard amount of propagules. The dense plug plant trial, which is located in the small pink catchment between Areas 1 and Area 2, received 36,550 sphagnum plugs, so that's around 5 per metre squared. 20 quadrats were located according to 2 main criteria. The first being on flat ground to reduce the likelihood of sphagnum propagules washing down the catchment during heavy rain events, and the second within 2 categories of topography, the first being undulating ground and the second being depressions or hollows on hagtops. In the topography trial, we set up 5 transects across gullies. Quadrats were used to monitor sphagnum species and area cover in 4 situations: gully floor, lower gully side, mid gully side and upper gully side. And I'll now hand over to Jemma, who will talk you through the results.
Thanks, Tia. The latest survey data here is the 2020 autumn survey, which brings us almost 6 years after the propagule application. We can see that sphagnum derived from plugs, translocated clumps and gel established and grew well over time. And the most successful types in terms of area coverage were plugs and clumps. Beads showed limited success. Simon Caporn's 2018 review of progress into sphagnum restoration using the micropropagated source material also showed that survival of beads was much lower than plugs on stabilised peat surfaces. A cost-benefit analysis has shown that when both sphagnum coverage and costs were taken into account, the most successful propagule type to date was gel, followed by clumps, plugs, and lastly beads. From the literature, Rubrick et al. In 2009 discussed that it is thought that the aggregate size of reintroduced sphagnum is important for performance, with larger patches better able to supply the capitula with water. Nine species from the plug mix established in the revegetated area in the propagule trial. The dominant species by mean area cover were Phalax and Palustri, which were 2 of the dominant species in the mix. You can see there in the table the relative proportions of the species that were used back in 2015. These results here come from the separate trial with dense plug planting. Firstly, sphagnum cover differed significantly between the 2 surveys, the 2 situations. That was tested for by a Mann-Whitney test. Limited growth of sphagnum from plugs was found on hagtop areas relative to the lower undulating ground by mean percentage cover. And by autumn 2020, the plug-derived sphagnum on the lower undulating ground areas where the water table was higher expanded to cover almost 80% of the quadrats. That's the purple line. We can now forecast from the results there of the dense plug planting that comprehensive sphagnum cover can be achieved in a minimum of 88 months when plug planting is delivered at a density of around 5 plugs per metre squared in revegetated areas. That's for planting on the lower undulating ground. It's the purple dashed line. A caveat to this trial is that mean plug plant density was found to be double that in the quadrats that were sampled, i.e. 10 per metre squared. And whilst there is more limited growth on the hagtop areas, we conclude that this does suggest that moisture from precipitation and cloud cover was sufficient for sphagnum to grow and survive. Grow slowly, really, in that extremity. Simon Capone et al. Discussed in their 2018 paper that it isn't certain whether a high water table is essential on Blanket Bog, as moisture arriving from above may compensate for a poor supply of water from below. The data presented here are from the gully transect surveys that were undertaken across the dense plug planting area. A one-way ANOVA showed the percentage sphagnum cover didn't differ between the 4 situations. Six species were found to have established from plugs in all 4 situations. They are Capillafolium, Phalax, Fimbriatum, Medium, Palustri, and Papillosum. So whilst subnitans occurred on 3 gully side situations, it didn't establish on the gully floor. Cuspidatum occurred on the gully floor and occurred once on the lower gully side. There was 1 occurrence of sclerosum on the gully floor and 1 occurrence on the mid-gully side situation. Looking at the mean sphagnum percentage cover data here, whereas previously it was frequency data, it appeared that sphagnum cuspidatum covered a greater area of the gully floor than the lower gully side where it was also present. A Mann-Whitney-Hugh test was conducted, and the results showed that there was a statistically significant difference between those 2 situations. We could also see that Phalax covered a greater area of the gully floor than any of the gully side situations, decreasing in cover up the gully sides. And one-way ANOVA showed that there were significant differences there between the 4 gully transect situations, as depicted here. Differences in mean area cover were also tested for between the 4 gully situations for both Palustri and Capillafolium, and no significant differences were found. Additionally, however, my colleague Mike Pilkington's work on sphagnum in Millennia shows a good representation of Capillafolium derived from plugs. There is research to show that this species is good at transporting water up its stem to keep moist, which is an adaptation to growing in these drier areas. So Mike's work indicates that Capillafolium, established in the Kinder Sphagnum trials, may show some effects of topography in later survey years as cover of the species increases. This year, we've also studied 11 of the moorland mixed species planted as single species plug samples in a separate study, 10 of which pictured here. Sclerosum was often contaminated with Phalax. Plugs were planted together in a square 6x6 configuration, and we found they were all suitable for planting as single species plug samples at the aggregate size. They showed higher cover increase in an Areophorum dominated study area than in a mixed moorland reference area, and also than in a dense Millennia dominated area. We found that these plug samples, they increased in area cover on average 8-fold over 16 months. That represents a 6-fold increase over 12 months. So in comparison with the Kinder trials, we found that the mean total area cover of the single mixed species sphagnum plugs that have been planted individually at a set density had increased 3-fold in 12-month periods. And this provides some evidence that the larger aggregate sample size of sphagnum plugs results in a more rapid growth in area cover than that for the individual mixed plugs that was trialled in quadrats in the Kinder trials. So to recap, a number of conclusions can be drawn from the propagule trials and from the single species study, and I'll leave those here with you. Further work underway at the moment includes miniature literature review to learn more about individual species niches. We aim to learn more to be able to further target the plug planting in order for single species planting to be feasible across the SAC. And we're also interested in how species interactions affect growth. Thank you for listening.
And thank you to Tia and Jemma for that really interesting presentation. It's really interesting to see the results, from sort of, I guess, real life use of micropropagation sphagnum for restoration. Next up, we are going to hear from Anna Keightley, who's a research associate in peatland restoration at Manchester Met University. Anna completed her PhD thesis at Manchester Met last year, in which she studied photosynthesis and growth of micropropagation sphagnum and gaseous carbon fluxes when this material was introduced to a degraded lowland bog as part of a restoration process. Really interesting. She's currently employed by MMU as a researcher on the Northwest European Care Peat project, and where she's recording and analysing greenhouse gas exchange on 2 UK pilot sites. One is an ex-mill restoration site in Greater Manchester and also a carbon farm pilot in Lancashire. And now we'll hear more about the Care Peat project in her video now.
Hello, my name's Anna Keightley from Manchester Metropolitan University, and I'll be talking today about the Marley carbon farm, which is one of Care Peat project's pilot sites in the UK. So the Care Peat project has a wide range of knowledge partners and nature organisations from 5 countries within Northwest Europe and is funded by Interreg. The UK project has 2 sites, one at Little Walden Moss, which is restoration of a bare peat site using companion planting, and the other site is the one I'll be talking about today at Marley Moss, which is conversion of a drained pasture to a carbon farm. So the Marley Carbon Farm is situated right next to Marley Moss, here on some grazed pasture, and both sites are owned by Lancashire Wildlife Trust. So the site is very close to Morecambe Bay, and it's surrounded by agricultural use, primarily livestock on grazed pasture, and the rainfall is just over a metre a year. So the Marley Moss sits on the edge of quite a large expanse of peat soils, which are quite fragmented and they're mostly drained for agricultural use. This, of course, oxidises the peat carbon stores and contributes to global warming through greenhouse gases. So why carbon farming? Well, grasslands are a small proportion of UK peatlands, but they emit a proportionately large amount of greenhouse gases. Re-wetting peatlands results in a reduction in greenhouse gas emission, but also protects existing carbon stocks. But reasonable economic returns are needed by landowners and farmers if they are going to convert to wetter farming or paludiculture or carbon farming. But there is a potential income stream through the crop and potentially through carbon credits, although the market development is still needed. So there are a couple of ways that we've explored recently of paludiculture in the UK. Sphagnum farming we've reported on before to the IUCN, and this delivers a high value paludiculture crop. But it needs more intensive management because there can't be any weeds in the crop, so you need weed removal, but also harvesting, processing. Carbon farming, on the other hand, has no removed crop, there's no till or fertilisers, but there's still the benefits of paludiculture in that there's a reduction in greenhouse gas emissions and protection of carbon stocks. But there's also potentially carbon accumulation over time and a greater biodiversity gain. So the Marley pilot site has introduced sphagnum as a kind of fast-track peatland restoration, but it also supports the neighbouring nature reserve hydrologically. So here is one of the peat cores taken from the site, and this is from the grazed pasture. The top section is the top 1 metre, and then we have the metre below it here. So you can see there's quite a dried, humified layer at the surface, and then there's a layer of dried and compressed sphagnum and fen peat, transitioning to more compressed fen peat. Then there's this saturated layer sitting perched on a woody layer, with a transition then to glacial clay. So this is the bulk density from samples of that peat core. You can see the bulk density is very high at the base of the core where we have the clay, and then partway up the bulk density is much lower in the wetted peat, and then at the surface on the grassland, which is this lighter green line, you can see that the bulk density is higher from about 30 centimetres below the surface, and certainly at the top. Analysis of the peat prior to any works on the carbon farm showed that the surface layers were quite high in nitrate, and ammonium levels were elevated as well. So it's decided to remove the top 10 centimetres, strip the top 10 centimetres, which would remove the nutrients, expose more acidic peat. It would also reduce the seed bank of agricultural weeds and take out the roots and any plant material, which would all help with promoting sphagnum growth. So here's a diagram of the carbon farm setup. This is a stripped area in the middle of the agricultural field. We have a sump area at the southern end, which pumps irrigation water through via a solar-powered pump down these irrigation channels on either side, and any overflow goes into the agricultural ditch, which drains the surrounding grassland. So the area is bunded and separated into 8 separate cells. There are branching irrigation channels here to make sure that each cell has adequate water supply. Our greenhouse gas monitoring points are here, the yellow dots here, and each monitoring point has a dip well next to it. So on the grazed pasture we have 3 monitoring points near the drain ditch and 3 a bit further into the field. And on the carbon farm we have a couple of points in what may be the dry areas next to the bund, and the wetter areas by the ditches, and then 2 that are kind of midway. We have a water table logger in each of the areas, so in the carbon farm and in the grazed pasture, and we have a weather station on the site as well. And this is what it looks like for real. So these are the main irrigation channels and the side channels. There's our weather station. There's somebody still planting sphagnum plugs by the looks of it. There were a lot to go in. So these are the little dots you can see are the sphagnum plugs, which were provided by BeadaMoss. And here is the surrounding agricultural land here. And the Marley moss itself is over on the right-hand side here. And this was in September 2020, so a year ago, when the site was first established and before the straw was put onto the site to protect the sphagnum. So for those who are not familiar with greenhouse gas analysis, this is our setup. So we have a Los Gatos analyzer, which monitors changes in CO2, methane and water vapour. It's connected by tubing to a series of chambers, creating a closed system. The chambers sit on a fixed collar in the ground, which is 30 centimetres across, and if fixed into the ground, half above and half below the surface. And here's the dip well with a cover on it. We also record daylight, levels of daylight, and peat temperature at the same time as monitoring the gases. So our methods, been through this bit already, we monitor greenhouse gas fluxes monthly from each collar, and each monitoring period is 2 minutes. At each visit we also monitor PAR, daylight, photosynthetically active radiation, and peat temperature and water table depth. And the weather station on site is measuring hourly PAR, peat temperature, and also air temperature and relative humidity. Again, for those who are not familiar with the way that we monitor greenhouse gas exchange, we're looking for the net ecosystem exchange, which is a combination of net ecosystem respiration from soils and plants and gross primary productivity, which is mostly plant photosynthesis. So net ecosystem exchange is expressed as a negative value if it's an uptake from the atmosphere, or a positive value if it's an emission to the atmosphere. So NER is always positive. Gross primary productivity of photosynthesis is always negative, but the balance between those two can mean that NEE can be positive or negative. Methane is usually an emission from the system. So this is how it's measured. We cover the chamber so that we get a measurement in the dark, which gives us NER, because of course there's no photosynthesis. And then we measure with a shroud over the chamber, which reduces the light by about 40% to simulate cloud cover. And then we measure in full light, which gives us the full NEE. So these are some of our carbon greenhouse gas measurements. So the measurements from the grazed pasture are here in blue, and the measurements from the carbon farm in red. So our grazed pasture looks like this. So there's a collar in the grazed pasture, and here is one of our collars on the carbon farm with the plugs, as you see, nicely growing there with a straw cover. So the values for NER are really quite dynamic from the drained pasture, and really quite low from, well, very low from the carbon farm. NEE, again, there are dynamic measurements from the grazed pasture, but as you can see, these measurements here are sort of between minus 0.6 and minus 0.2 NEE, but NER is much higher. So already you can see that there's that the grazed pasture is a source of greenhouse gases. Methane is actually methane emissions are very low on both of the sites, a little higher on the grazed pasture during the winter. In the summer, it looks as though there's an uptake of methane from the atmosphere, but actually it's likely oxidation of the available methane by methane oxidizing bacteria. And our sphagnum has grown quite well in the covers, so we've now got about 0.25% of the collars covered, but it's not really quite as much as we'd have liked every year. So this is an example of how we model the greenhouse gases that we've measured. It's a basic sort of iterative process of incorporating the primary, secondary and tertiary environmental drivers of the changing greenhouse gases, and extrapolating this into a predictive model that we can fit against the hourly environmental variables that we measure on site at the weather station. So just as an example, this is data from the GPP on the carbon farm across a 6-month period. As you can see, fitting a regression line against peat temperature gives us quite a high R² value. So that's our primary driver. Our secondary driver is PAR. You can see the R² value is smaller there, but still reasonable. And then the tertiary driver is the water table depth, and the R² value is lower then again. So we put all those together in a model and check that the model is a good fit by plotting it against the measured values. And here you can see the fit is we have quite a high R² value here. There are some outliers, but it's a reasonable fit to be reasonably confident that our model values are right, and that model will improve the more data we feed it. And this is what the results are from this particular set of values. So the blue lines are the modelled data, and here are the measured data points, and as you can see, they sit quite nicely within the modelled data. So looking at the annual carbon budget, Both systems are currently carbon sources, but the grazed pasture is emitting 10 times more CO2 than the carbon farm currently. And that's because it's drained and cropped and fertilised by sheep, and so there is a high NER. The carbon farm is still mostly bare, wet peat, and so GPP is low. But we're expecting that it to become a CO2 sink once we have a full cover of sphagnum. So the carbon loss, we can estimate the carbon loss from the pasture and put that against the carbon stock and show that we may have a complete peat loss in just over 100 years or a couple of generations. But the precision will increase over time in the modelling. So here's a quick look at the water table depths in both the grazed pasture and the carbon farm. As you can see, it's really very low here in the warm, dry months on the grazed pasture. It's actually lower than we'd like over summer as well. On the carbon farm, we've had some problems with the irrigation system, and at the moment it's below the 10 centimetre threshold for carbon retention. So just to sum up, stripping the grazed pasture and re-wetting it has resulted in an immediate reduction in CO2 losses, and that removed peat can be used elsewhere on the site to reduce carbon losses. Peatland drainage obviously causes a loss of organic soil and productive land over time. Raising the groundwater levels doesn't necessarily affect neighbouring drained land for farmers who want to continue with traditional farming. Maintaining a high stable water level and producing a sphagnum cover over a short time scale has been difficult on the carbon farm. And there are some ongoing problems. We have competitive weeds, which just need trimming down to allow the sphagnum to grow, and we've still got problems with the. So our ongoing work will be to carry on with monthly greenhouse gas measuring to create annual budgets, and we've been participating in stakeholder engagement events organised by the Lancashire Wildlife Trust, and we'll soon be starting monitoring potential methane losses on the ditches on the carbon farm using this floating chamber. And thank you very much for listening.
Thanks, Anna, for another great video. Obviously, I must admit I'm involved in this carbon farm as a member of Lancashire Wildlife Trust, but I really think that the results that you're seeing, although initial ones, show real potential for this kind of activity and to play a part in the battle against climate change. So last but not least, we're going to hear shortly from James Brown, who's director of Pollybell Farm. Pollybell is a 5,000-acre organic farm which crosses 3 county borders, Nottinghamshire, Lincolnshire and South Yorkshire. And Pollybell really is looking to lead the way in sustainable farming practices in the UK. And in the next video, James will be sharing his experiences of farmed lowland peat.
Good afternoon, I'm James Brown from the Lapwing Estates, Pollybell Farms, and I'm going to talk to you today about a project called Reverse Coal. Now, just a little bit of background, this presentation and the work which we've been doing has been funded by the Department for Business, Energy and Industrial Strategy and is a feasibility study at this point looking at how we can capture and sequester carbon. We've been working with the University of Lincoln and also the UK Centre for Ecology and Hydrology. So, an introduction to who we are. The Lapwing Estate owns 5,000 acres of freehold organic land in Nottinghamshire and North Lincolnshire. So this is at the bottom of the Humber Head levels. And the business includes the organic farm, and we started the conversion to organic in 1997. It also includes a renewable energy business called Lapwing Energy, a shop and fine foods business called Browns at the Buttercross, and an agri-tech startup called Frola. We are, as I just mentioned, at the bottom of the Humber Head levels, so we're east of Doncaster, sort of near the M180, M18, and the land is predominantly flat, so we go from -1 metre below sea level to about sea level. And I think the thing which is really important just to highlight is that we're one of the regions here which, in terms of jobs, is most at risk, has been highlighted as being at most at risk to the decarbonisation agenda. So the Yorkshire and Humber region has some of the highest per capita carbon emissions because of the industry which is still here. So a little quick history. I'm the 5th generation to be involved in the business, and our business has constantly evolved. So my great-great-great-grandfather, William H. Brown, started off with a family farm in Mid Lincolnshire, and he went into straw and hay merchanting, which developed into a agri-chemical agronomy business, built up to one of the largest private businesses. Then in the mid-90s, despite having a agri-chemical business, my father decided to start converting some of our own land to organic, and the first job I did when I joined the business was actually to sell off that agri-chemical business and focus entirely on organic farming. So as you can see, we have done some quite radical changes, and we will constantly respond to the needs of the time in how our business operates. And it's also just important to mention that we are a commercial business, we have shareholders, and it's our job to generate a profit for them. But at the same time, we have a long-term view on how that should be. So the problem. Now, everyone knows all of this, but I just thought I would highlight very quickly. We're looking at, first of all, the fact that obviously humans have put 2,400 gigatons of carbon in the air to date, which has led to a 1.1 degree increase in temperature. And the UK is the 5th largest polluter over time. And therefore, that's why it's so important that we feel that we should come up with innovative ways of solving this. I also think it's really important to note that if we look at the UK's imports are responsible for more CO2 emissions than any other country in Europe. So, as the IPC have highlighted, we need to sequester carbon and to keep the global warming limits less than 1.5 degrees. And at present, the recent McKinsey report has shown there's about an 80% shortfall in the pipeline of negative emissions technologies. If we look at the UK, agriculture and associated land use is about 11% of emissions, and Lowland peat accounts for about 3% of all of those emissions. So we obviously need to stop those emissions, which is carbon abatement, as well as sequestering carbon to get to net zero. I just think something which I found very useful just to show to people who are new to the space, which I know none of you are, is this whole thing that we can't get to net zero via abatement alone, that we need to add sequestration. So our project is primarily looking at both of these parts, avoiding emissions through abatement and also sequestering carbon. Now, the two sides of lowland peat farming, obviously peatland is highly fertile to grow crops on, and interesting, 60% of all UK farms are vulnerable without the Common Agricultural Policy. However, the lowland peat farms, which are used for fresh produce, and about 1/3 of all UK's fresh produce comes from those farms, are actually the more profitable farms. But on the other side of that, the drainage and cultivation has led to the huge quantities of CO2 release, and also that oxidation, as I said in my introduction, has led to the lowering of land. So these are the sort of two challenges, is that we've got this situation at the moment where it is very good land and highly productive farmland. So just to give you a quick introduction to why we even started looking at carbon. Back in 2011, we got involved in the Soil Association, so our organic body's low carbon farming project. And that identified the sources of emissions and helped sort of us create a plan. And we've installed things like the floating solar panels you can see in the picture, wind turbine. We've changed the tractor fleet. We've retrained staff, changed working practices, moved where a tractor shed is, and that by 2020 had halved the emissions. And I won't lie, I was pretty smug about this and felt, well, that's certainly something to be proud of. And I think, just as an aside, it gives me a lot of confidence of the possibility of how we can actually reduce emissions in agriculture more widely. However, in 2019, the DEFRA team kindly introduced me to Chris Evans and his team from UKCH, and Chris, Neal, Davey and Ross came up to see me, and I proudly told them that we'd taken our sort of 1 tonne of baseline emissions per hectare down to about a half tonne. And Chris said, well, that's wonderful, James, but you realise that if you've got deep peat here, it could be emitting 35 tonnes a hectare per year, and even wasted peat could be up to 25 tonnes a hectare a year. So with the best will in the world, everything you have done is pretty meaningless unless you alter your land. And I said, well, how do I stop those emissions? You need to wet your land, at which point I said, that means I've got to stop farming. So that was sort of our introduction to carbon, which was this fundamental problem of, I want to keep using my land for productive agriculture. We'd gone organic, thinking that was a way to be sustainable. We had started tackling our direct emissions, but we simply didn't understand the impacts of the peat. So this picture in the bottom right corner shows is a flux tower which Chris and his team, Ross and his team have installed now on the farm. So it is actually now measuring what our land is emitting. So what's our solution to this? And this project, which we call Reverse Cold. So the first thing is as Chris had made very plain to me, I need to re-wet my land. And so we're going to look at abating those existing emissions. Now, based on the national inventory, which is about 26 tonnes per hectare per year for lowland peat, that would be 1,300 tonnes per hectare over 50 years, which is, based on the core samples we've done, a good approximation of how much carbon could potentially be released from our soils. And that in its own is obviously going to generate some new ecosystem services. So we've got biodiversity net gain from that, flood alleviation, water resources and quality management. We're in the Idle and Torn catchment, which is one of the priority catchments for the Environment Agency, where there is both over-abstraction and flooding. And I think that was really brought home to me in November 19, when we had a little bit of the farm flooded, and there was substantial floods in Retford, Worksop, Portree, Doncaster. And then in May 2020, we got a notice of potential to turn off abstraction licences due to low river flows. The Idle and Torn is also failing from a water framework directive because of water quality, so there's a real potential there. Also, our land was car land, and so CARR, and that it would have been wet woodland, and that was obviously all disappeared when Charles I ordered Glamorgan to drain the land some 400 years ago. And I think that's where we started. So the first thing which I did was to say, what was this land before it was drained, and does that give us any ideas about what we could do? So our idea is to establish polyculture and grow biomass. And for example, that's going to be short rotation willow coppice, it will be reeds, and Chris Evans and his team have got a project starting this year at the farm here, where we are going to be growing different trials of polyculture to look at which one of those will be the best for energy production. So what our idea is, we grow the biomass, we harvest it, and through pyrolysis, turn that biomass into energy and biochar. We bury the biochar back on the land to sequester carbon and rebuild that land, which will also enhance water filtration. And we use the energy for high-tech controlled environment agriculture, and that will also enhance food security, reduce imports, help solve the seasonal labour crisis, which is currently in agriculture and horticulture in particular, but also give some opportunities to improve food quality and nutrition. And so at the heart of this whole thing is bioenergy, carbon capture and storage, or BECCS. So here is a diagrammatic version of what we are planning on doing. So on the left-hand side is the current bit, and as you can see, the big emissions actually come from the peatland. And what we're going to do is solve that by raising the water table, and we are going to effectively grow biomass and turn it into energy, which we turn into the food, and bury the biochar back in the land. So we moved from 1 hectare of drained farmland emitting circa 25 tonnes of CO2 per year to 1 hectare of lowland peat under our system generating biomass that produces 6,000 kilowatt hours of electricity, 10,000 kilowatt hours of heat, and sequesters 3.1 tonnes of carbon. So what's at the heart of it? How do we capture carbon? Well, it's a natural system, photosynthesis, I'm sure you're all aware of, but I've included it because it is the basic way that people ask me, well, how are you getting carbon out of the atmosphere? Well, we are using this process. Now, we could burn that wood to generate energy, but obviously all of that carbon would end up back in the atmosphere. So whilst that would help abate the carbon, it doesn't actually sequester any. So instead, we've looked at pyrolysis. And so pyrolysis is the heating of an organic material in the absence of oxygen. So think charcoal making. And what we actually do is, as we heat it, it gives off various gases, syngases, which we burn to generate electricity. And the byproduct from it is biochar. So the greenhouse gas removal isn't the total amount of carbon that ends up in the trees, but instead it's the amount of carbon which is in the biochar which we bury. So what scale are we looking at? Well, we're looking here at 35,000 hectares of polluticulture generating some 315,000 tonnes of willow. Now, we've assumed that we won't be planting obviously every hectare, there'll be about 10% which isn't planted up. But that sounds a huge amount. But what I'm trying to do here is move the needle and actually create a huge demand for polluticulture crops in the form of energy crops. And, you know, it sounds a lot, but actually, if I put it into some form of context, British Sugar, they grow 100,000 hectares, or growers grow 100,000 hectares of sugar every year. They move 8 million tonnes of sugar beet into their factories. So it is something which has been done in the landscape before. So then where do we store our carbon? As I mentioned, we generate electricity, we generate heat, we generate biochar. And it's this biochar, which is about 86% carbon because we're treating it at 800 degrees centigrade. And what our plan is to rebuild the land. So our land over the last 400 years has dropped by about 4 metres. And in the last 40 years alone, the measured loss based on core samples is about 24 centimetres. So as I say, our concept is to refill this hole with biochar, and as we rebuild the land, so we keep raising the water table up, because at the moment we're in a completely pumped system where the water is below, the land is below the river levels. Now, Professor Evans has estimated there's 2,000 megatons of CO2 storage in the UK lowland peat. So that is this hole that's been created over time through the oxidation. Some of the challenges, which I'll just quickly talk about. First one is access to water. We've been trialling how we re-wet fields, and we've had an absolute headache trying to, even though we have substantial irrigation licenses, getting permission to use those to re-wet land. And I think the second biggest challenge we've got is how on earth to all the different benefits, so biodiversity gain, water quality gain, flood alleviation, how we actually layer those ecosystem services and monetize them to generate an income, because willow on its own is probably going to be less profitable than growing a vegetable crop. However, when you add in all those other benefits, we think it can challenge in terms and persuade farmers to change their land. And the other bit is that one of the challenges we've got is the establishment of polluter crops, and a number of the ways of establishing willow, for example, use lots of glyphosate and post-emergent herbicides, which as organic growers is something we really want to avoid, and particularly if we're going to be wetting it. So just to explain here, I mentioned our agri-tech startup Earth Rover. We've patented a lightweight, so less than 100 kilo autonomous rover, and this kills weeds using concentrated light. So we think this could be something we can adapt to polluter, but it's going to be some of the challenges we face. The equipment that is available has been designed for dry agriculture, and we're going to have to look at how we change those for wetland agriculture. So in conclusion, I just want to finish with a quote from Lord Devon. Obviously, land use is going to have to change urgently, and it's time for radical change. And for us, we want to be inspired by the past and the Carland heritage that this area was, and believe that that actually offers an interesting opportunity, and the use of wet woodland to create energy could create the demand to really scale polluter. Thank you very much.
Thanks very much, James, for another really interesting talk. I mean, it's such a interesting field to look at. Wet farming and polluter as a way forward for sort of alternative management of lowland peats. Really interesting to hear what you're looking to do as well. I love the idea of that automated rover, because that might be useful for weeding on the carbon farm, wouldn't it, Anna? We've had obviously 4 really interesting videos, and lots, which is, for me, I've got loads of questions, and there's been quite a few questions coming in from the people listening as well. So we can move on to the Q&A session now with everyone. So with me, we still have obviously Anna from MMU, we have Tia from More to the Future, James is with us from Pollybell, and we have Andrew and Neal from BeadaMoss. As I say, we've had quite a few questions in. I'll see how we can get through them in the next 15 minutes. Then anything that we don't manage to answer, we'll put them on the conference message board as well. So the people who are listening, they've been sort of voting up questions that they like the most. So I think I should really start with the top one. And the first question that's come in is, what is a threshold for deciding when to let sphagnum colonise naturally once water levels are stabilised versus inoculating with propagules? And I think I'll come to you, Tia, first. In your experience with More to the Future and restoration, have you ever had to make that decision? Okay, when do we let things naturally colonise once the re-wetting's done, or when do we need to have that added intervention and inoculate as well?
Hi, we've not really got to that stage yet, because in the Peak District in the South Pennines, because of that legacy of the Industrial Revolution and all of the air pollution, all of the sphagnum moss was killed off. So there isn't really a source for sphagnum to naturally recolonise from. The more restoration that we do, the more of these sites that we get sphagnum established onto, then that sort of thing might start to happen, but we haven't got to that stage yet.
Yeah, absolutely. So I guess it really depends. It's quite site specific, really, to what is naturally there already versus if it needs that added intervention to kickstart the restoration process with vegetation.
Yeah, absolutely.
Yeah. Okay, that's great. That's a really good answer. The next question we have here Next most popular question was, please can you explain more about the comparison of coverage and photosynthesis data for Beda hummock and wild clumps? I don't know whether it's another question for you, Tia, and or whether I guess Anna and the guys at BeadaMoss might be to look at that. Do you want to have a stab at it first, Tia? Do you need me to read the question again?
Oh no, I'm not sure that's one for me. I think that might be more BeadaMoss or Anna, I think, to answer that one.
Okay, Neal.
Okay. Yeah, I think the graph referred to was looking at the percentage increase in cover. So it was based on the starting coverage and its increase in area as time went on. The photosynthesis data was something that Anna did as part of her thesis, looking at comparing wild collected sphagnum with micropropagated sphagnum, and found the photosynthesis rates of all species seemed to be much greater if they were micropropagated.
Hannah, do you want to comment on that question as well?
I didn't actually see the graph. I think I remember from PhD days. Yes, just to reiterate what Neal was saying, really, was that there was greater photosynthesis in BeadaMoss sphagnum than in wild sphagnum across the board, really, and part of that is related to the fact that it's new and vigorous, and so it's growing more quickly, and so taking up more CO2. And there are also because of the way the material is produced and grows, it grows with more capitula. So there's just a greater amount of sphagnum to actually take up CO2. So when sphagnum is mature in the field, you get large heads, and it's probably spread out quite a bit. But the plugs, the BeadaMoss material, has a very large number of growing points. So I think that's part of the explanation as well.
So would you expect that over time the differences would reduce between the two, or because of how you explained, would it continue to have that sort of difference for the Beda hummocks?
I think that's one of those things that we haven't been growing it long enough to see exactly how it declines with age. I would also introduce the fact that the micropropagated sphagnum is sort of juvenile. One of the things found with all micropropagated plants is that they act like juvenile plants, and they tend to be more vigorous. And I think one of the things that Anna found was that it contains more chlorophyll, which for some reason, I don't know whether that relates to its juvenility properties, but it seems more vigorous as a consequence of that.
Yeah, so it'd be interesting to see, I guess, as we get more data, more longer term data, to see how this progresses. But a really interesting question, actually.
Sorry, just one other thing with that is that the important thing is that it gives the BeadaMoss a real big kick right at the beginning, and it's much more likely then to spread out and cover an area and be beneficial for restoration than if you were to take clumps of material that's still on the site, which would then need to recover and then start to grow. So it's beneficial.
Yeah, that's really interesting. I mean, one other question. Oh yes, Tia, you want to come in on that as well?
Yeah, just to add in on that. So we saw when in the trial that Jemma was talking about, the translocated sphagnum, that initially we did a survey quite quickly after it had been planted, and initially there was a slight drop off in size before it recovered. So what Anna was saying about, it causes it some stress being harvested and then moved and planted somewhere else, which you don't seem to get quite as much with the plugs.
So going forward, would that influence your decision on what source materials you would use? Would it be default going to always like sourcing material from around the site if possible, or would that, the fact that the micropropagated plugs are more vigorous, for example, would that influence your decision on what you would use going forward?
Yeah, I mean, I think there are obviously other advantages of the plugs as well, because you've got some control over the species that go into the mix if you're harvesting, and maybe not so much in the future. You know, if we've got a lot of sphagnum cover, then there may be more species on the site as well. But where we've used translocated sphagnum, it's been largely of a single species, and that species then might not be quite as suited to where it's being moved to. So, yeah, I think for the foreseeable, I see us using the plugs, until there's a lot more sphagnum established on sites.
Yeah. What's the difference in costs? What's the magnitude of difference in costs of taking the source material from, out on site versus using micropropagating material?
Yeah, so again, Jemma touched on that a little bit. So we did a cost-benefit analysis. Now, this is based on costs from going back to 2015, and I can't remember the actual costs off the top of my head. But based on cost and on success, then she said in that presentation, the gel was actually the most successful, then clumps, then plugs. But the plugs still have a number of advantages over the other forms of propagules. So particularly if we talk about the gel, with that being the most successful, but it's actually quite difficult to apply. So in our trial, it was fine. We actually used, I think it was a syringe that we used in the end, so you could actually get it right down onto the peat. But I think initially the ideas were that it could just be sprayed, but then the gel would end up on the vegetation and it would dry out before it made contact with the peat. So we don't, I think, have a very effective method of applying that over a large area. Obviously, we've talked about advantages of the plugs over the clump. So even though, based on it's just based on cost and coverage, the plug isn't coming out top, but it's got lots of other advantages, which mean that is what we will use.
Yeah. This is really, I think there's so many more questions we could talk just about this particular sub question of this, but I really, I'm just looking at the time, and I would like to also come to James as well, because there's been quite a few questions coming in, James. I don't know if you can see the chat as well following your talk, which has been well received. One of the things, and I was interested about this as well, you talk about the biochar. And then one question that's come in is that what impact does burying the biochar have on the peat? Has this been looked at yet within the experience that you're doing?
Yeah, so it's actually UKCH kind of doing, those experiments are ongoing at the moment and is part of it. What you're going to be aware, the land we're on, some of the area with this wasted peat, you're going from virtually zero peat left, so it's nearly fully almost a clay soil in places, right up to still deep peat. So there's a huge variability, and the same applies across down in the sort of Cambridgeshire Fen areas. So I think that we are looking at that and what impact, and whether the advantage of raising the water table actually offsets that any potential damage. Because I have obviously read about the potential downside of putting dry biochar onto dry peatlands and the impact that would have. So it's something which we don't know the answer to at the moment, but is an ongoing experiment which should be done in the next month or so to finish off.
Oh, right, that'd be interesting. So watch this space then in terms of some answers to that. I mean, there's also been a couple of questions for you around the sort of financial requirements or figures to sort of support this reverse coal approach. Are you able to touch on that briefly?
No, I mean, the project we're looking at, bear in mind, we're talking about doing this at a very substantial scale, and the whole purpose of it was to, between both abatement and sequestration, to look at a megaton of CO2 removal per annum. We are looking at about a 1.2 billion investment in total. So it's trying to, because the whole thing from my thought process on this is, how do we end up with a project which puts itself in the space of institutional investors, the pension funds, and actually enables them to produce a return which works. And the other reason the project is so expensive in terms of it does include the controlled environment agriculture, which, because the biggest criticism which farmers often levy is where's the food coming from. So I've been very keen to be able to show that there is an alternative, a better food production system by using a combination of vertical farm and glass. And yeah, that's why it is. But also, because the carbon price is so uncertain, it's actually uninvestable at the moment. So we've been trying to design a model whereby should the carbon price not be where it's predicted, there is still a return. It might not be as good a return, but there is still a return to investors.
Oh, sorry, I think I froze for a minute there. Sorry. That's so interesting. I'd love to come and visit. And myself and see, and I know other people in the chat have said they'd like to come down. So there could be some visits coming your way in the offering, James. I'm afraid we've run out of time. It's 2:45 already, and there's so many more questions that have come on and I'd have. But yeah, as I say, those questions will get put onto the conference notice board. So hopefully, maybe if you have a chance, any of you can sort of have a look and pick any other questions up if you have time. That'd be fantastic. Otherwise, thank you very much, everyone, for taking the time with your fantastic presentations and joining us for the Q&A as well. And I wish you all the very best with all your various adventures. And thank you very much for everyone for listening in. Thank you.
Thank you.